Alright, let's look at graph 1 here. If we look at graph 1, we see it's labeled nicely. The axes are labeled, but if you notice, what they don't have is the units identified like we do in other graphs. So the problem here is we should have units. So in that case, what we have here is, it is D. The axes are improperly labeled. Let's look at graph number 2. The problem with graph number 2 is the way it just goes all over the place. What we really want to have is a nice straight line like this. Now, that's not a very straight line, but you get the idea. It should be a straight line or a smooth curve. So the problem we have there is C. The best fit line is improperly drawn. If we look at graph 3, the problem we have here is that all the data lands within the first maybe 1/4 of this axis. So what's happening is we've scrunched everything down into a low area. We really want to have this more up in here. So the problem here then is that the range of the graph is wrong for the data, which would be B. So for 4 through 6, what we're going to do is we're going to identify the relationship. And if I look at graph 4 here, what I notice is that it follows a curve upwards. So because it's not a straight line, it's not a proportional relationship, this is an example of a power relationship. Now, power relationships can look different ways. They could look like this, or they could look like this, but it's going to be curved and moving upwards. If we look at number 5 then, 5 is basically straight across. And notice there's a little bit of up and down movement. There's some scatter in the data, but there's always scatter in the data. Basically what we see here is there is no relationship. No relationship. Okay, and then if look at my writing, that's terrible. Okay, now look at graph 6. Now when we look at graph 6, what we notice is we have this downward swoop. Now this downward swoop could either be inverse or inverse squared. So we look here, we see the equations begin y equals a over x squared. So this is an inverse square relationship here. Inverse SQR. We'll do it that way. Alright, for number 7, the question is, what is the independent variable? Remember, the independent variable is the one on the x-axis. So in this case, what we have is airspeed. What type of relationship exists between the variables? I see it has a downward trend to it, which means it's either inverse or inverse square. So I look at the general equation, and I see that it's y equals a over x, not x squared. So therefore, it's just an inverse relationship. So here we'll say inverse. Number 9 is asking us what is the specific equation. So the specific equation, let me move this a little bit. The specific equation we get by taking this one here, y equals a over x, and substituting the y, the a, and the x. You have to substitute all of them. So let's start with y. Here's our y-axis. So we'll say pressure equals, instead of A, we're going to go here and see this is what A equals, 6.043. So we'll say 6.043. When we look here, this little slash really means over. And instead of writing x, we have to look and see what the x-axis is, and the x-axis is airspeed. So we're going to go ahead, and here we're going to write airspeed. Now, what we're going to do is we're going to use this specific equation to find the airspeed when it's 500 km. So that means we're going to substitute 500 for airspeed and use the rest of the equation. So I'm going to abbreviate and just say P for pressure equals 6.043 divided by, and I'm going to go ahead and take this 500 and put it in here. So I'm going to say over 500. I'll worry about the units later. Now when I go ahead and divide that, what I get is that, I get P equals, in this case, P is going to equal 0.012 atmospheres. And I know it's atmospheres because if I look at the y-axis, which measures pressure, here's pressure, whoops, we see that pressure is measured in atmospheres, so that's why I put atmospheres here. Now, let's look at our next one. Our next one says to use the specific equation to calculate the airspeed. So now I'm calculating airspeed, and I'm going to be given the pressure. And the pressure I'm given is 0.08 atmospheres, so I'll substitute in. For P, I'll put 0.08 equals, notice A is always the same, it's a constant, it's 6.043 divided by, and let's just call airspeed AS. Now what we're going to do is, when we're solving for a variable in the denominator like this, we want to swap these two variables here, is how we're going to get started. So I'm going to rewrite this equation this way. I'm going to say airspeed equals, that's a terrible equals, 6.043 over 0.08, and therefore airspeed equals 76. Now I want to know what the units are, so let's look. If I look here, airspeed's units are kilometers per hour. Oops, I moved the wrong thing. Let's try again. Is going to be kilometers per hour. And please always remember to keep these units in there. They do matter. Now let's see what it says next. It asks us if the RMSE value had been 6.85, would it have been closer to or farther from it? So what we need to do is, the smaller this number, the closer the points are to the line, the larger this number, the farther they are from it. So let's compare 6.85 to what we actually have here. We see the RMSE value here in this graph is 2.54, which is closer to 0. So what that tells us then is, since this number here is larger, it means that they would be further from the line. What is the dependent variable on this graph? Well, let's take a look at the graph. The dependent variable is the one that goes up the side, so in this case it would be distance. I'll just write dist. Oh, I'll go ahead and write ants. Okay. What type of relationship exists between the variables? Well, if I look at it, I see there is definitely an upward curve to it, and that is indicative of a power relationship. Now let's see what we've got next here. What is the specific equation? So remember, to do the specific equation, I've got to substitute out both the y, the a, the x, and in this case the b. I have to swap everything out. Nothing can stay the same. So my y variable is distance. I'll just write d equals. Instead of a, I'm going to go here and see a is 0.64. 0.64, and it is times x. Now x in this case is time, so I'll go ahead and say t for time, and I'm going to raise it to the power of, so if you notice here it says raised to the power of b, and b is 2, so I'm going to say squared. D equals 0.64 times t squared. Now the next thing I do is I'm going to use the specific equation to calculate the distance. I'm trying to solve the distance given a certain time value. So I'm going to take the time value and substitute it in here. So what I'll have then is D equals 0.64 times 22 squared, and that means that that's the same thing as saying D equals, I gotta look this up, 309.76. And what I want to do is I want to round this to two significant figures, because I have two significant figures here. So that rounds to 310. In this case, the distance is measured in meters. Don't forget your units. Now, let's see, number 17 asked me to use the specific equation to calculate the time. So in this case, what I'm looking for is I'm going to use this equation here. Whoops. I'm going to use this equation here, but I want to solve it for the time. So, let's see, my distance is 135 meters equals 0.64 times t squared. That's a terrible t. So my strategy is I'm going to undo what's being done to my variable. So if my variable is t, it's being multiplied by 0.64. The opposite of multiplied by 0.64 is divided by 0.64. So both sides are going to be divided by 0.64. So this just becomes a 1. And what that gives me then is that 135 divided by 0.64 equals 210.94 equals t squared. Now I have to undo what's being done to t. T is being squared. The opposite of squared is square root. So I'm going to take the square root of this, and I'm going to take the square root of that. And what that's going to tell me then is that the value for t equals the square root of 210, and that is 14.5 seconds. Okay, the independent variable in this case is distance. The type of relationship I notice is a downward curve, so it's either inverse or inverse squared. I see that the x is squared, so in this case it's an inverse square relationship. The specific equation, I'm going to substitute out all these values, so I'm going to say magnetic force, that's my y, equals A is 7, I'll forget the 0.001, divided by, instead of x, I'm going to say distance, and I notice that it is squared, so I'll go ahead and say d squared. Now, if I use the specific equation to calculate, let me move this out of the way, a distance. So I'm going to try to calculate a distance. This is a tricky one. Let's try this here. So the magnetic force is 96 equals 7 divided by d squared. So my trick is, if I'm solving for a variable in the denominator, I'm going to swap these out. So I'm going to rewrite this as d squared equals 7 over 96. And then I'm going to go ahead and divide that. So that means that d squared is equal to 0.0729, but I don't want to know what d squared equals. I want to undo squaring, and the way you unsquare something is by taking the square root of that, but that means I also have to take the square root of that, and that's going to give me d will therefore equal 0.27 meters. Now we'll finish off with the easy one. Okay, so now I want to find the amount of force at a given distance. So the magnetic force is going to equal 7 over 0.15. Don't forget that it is d squared, so you've got to remember to square that there. What that means, therefore, is that it equals, magnetic force equals 311.155 newtons, but since I only have two significant figures here, I'm going to round my answer to two significant figures, and I'm going to write that 310 newtons.